We have two speakers today. Those speakers are Janna Lipenkova from Anacode and Joe Toplyn, who I don't do extensive introductions because that's kind of false. Let the speaker introduce him or herself. I will let Joe introduce himself and take it over now with a talk that should be really interesting on computational humor. Joe, I would invite you to start by giving a short bio. I don't know whether you have a slide that covers this, but if not, tell us about your background in comedy writing.
Well, I do have a slide on that, so maybe I'll just dive right in.
Go ahead. You should be able to start sharing your screen. So once again, attendees, you can enter questions via the Zoom Q&A function, and you can also chat to send your questions just to the panelists or to one another for that matter if you see someone in the attendees list whom you want to interact with. So take it away, Joe.
Thank you, Seth. I'm Joe Toplyn, and I'm going to be talking to you about Witscript, which is a new approach to computational humor. I define computational humor as teaching a computer how to recognize jokes and also generate jokes. And I've read that some researchers consider computational humor to be a holy grail of artificial intelligence. So here's a little bit about my background. I studied engineering, but pretty quickly went into television, and I wrote a lot of comedy for late night shows like David Letterman shows and Jay Leno's Tonight Show. Later on, I wrote a book about comedy and taught myself how to code and became a humor engineer. So unlike almost all other researchers in computational humor, I've actually written a lot of comedy professionally. Next. Sorry, I'm having trouble advancing. I'm having trouble advancing.
Your bio slide.
So, there we go. Okay, so there's my book. It's called Comedy Writing for Late Night TV, and it answers the question, how do humans write jokes? Which I think is the first time that question has actually been answered in such detail. I think answering the question, how do humans write jokes, removes a roadblock that has slowed down research into computational humor. The book is full of algorithms and techniques and rules that humans use to write jokes. And I'll show you some of those algorithms now with some examples. Here is an actual joke that was written by a human and told on one of the late night comedy shows. Ben & Jerry's has announced a new flavor based on a popular TV show. It's a nice idea, but I'm not sure that people are going to want a scoop of Law & Order Special Victims yogurt. All right, how was that joke written? Well, the first thing that the human writer did was pick out two of what I call topic keywords from the topic sentence. Those are, the two topic keywords are words that are the most interesting elements of the topic sentence. They're the words that stand out the most. They're the most distinctive elements. In this case, they're Ben & Jerry's and TV show. The fact that those two elements are in the same sentence makes the sentence interesting. The next step that the human followed was to take one of the topic keywords and free associate on it. To ask the question, what do I think of when I think of Ben & Jerry's, and make a whole list of those associations mentally. In this case, yogurt was on the list of associations. The next step was to take the second topic keyword, TV show, and generate a lot of associations for that topic keyword. In this case, that list has a lot of TV show names on it. And one of those TV shows is Law & Order Special Victims Unit. So to create the punchline, all a human writer did was take out unit and replace it with yogurt. And there's some wordplay between yogurt and unit that makes that a nice substitution. And that's how the writer got Law & Order Special Victims yogurt as the punchline. And the final step in writing a joke is the human writer created text to bridge between the topic sentence and the punchline that he or she just created. So the bridge is language that makes the whole joke read like it makes sense, like a natural statement. Here's another example of an actual late night TV joke. In Japan, a produce company is selling Mozart bananas, which are bananas that have ripened in a room where Mozart is playing. The company hopes that their Mozart bananas go over better than their Sir Mix-a-Lot yams. Okay, that joke was written in a very similar fashion. The two topic keywords were Mozart and bananas. Mozart has as one association another musician, Sir Mix-a-Lot. Bananas has as an association yams, another item of produce. And to create that punchline, the human just juxtaposed Sir Mix-a-Lot and yams, just put them one right next to the other, and then filled in the middle of the joke with a bridge. The final example I have is the newest craze in book publishing is novels about the Amish, which explains the #1 New York Times bestseller, How Jebediah Got His Groove Back. This was written in pretty much the same way. The two topic keywords are novels and Amish. Novels has as one association the name of a novel, How Stella Got Her Groove Back, and Amish has as one association the stereotypical Amish name Jebediah. So to create the punchline, the writer just substituted Jebediah for Stella. Oh, and sorry, I'm having a little trouble with the audio, but maybe it's okay. All right, so what are the key points that I have been trying to make by analyzing these 3 jokes that were written by humans? Well, one of the key points is that humans actually do use algorithms to write jokes, and we saw some of the algorithms just now. Another point is that some of those human algorithms don't require common sense reasoning. So the jokes that we just analyzed don't require knowledge of the just common sense, the ability to reason. They don't require artificial general intelligence, in other words. Some of the human algorithms just rely on wordplay, like the ones we just saw. And those human algorithms can also be executed by a machine. So that brings me to Witscript, which is the first artificial intelligence to improvise original, contextually integrated jokes. Improvise meaning the software creates the joke on the spot. It doesn't just take it from a database of stored jokes. The jokes are original, they're written for the first time then and there, and they're contextually integrated, meaning that they are based on the context that the joke is in. For example, during the course of a conversation or dialogue. Witscript mimics the human joke writing process, basically the process that we just saw that was used in writing the jokes, the late night jokes we just talked about. Witscript is self-editing, meaning that Witscript doesn't just generate a lot of gibberish and then require a human to curate the output and to find funny parts of the output. Witscript has an internal system for scoring jokes, and it only outputs jokes that score above a certain threshold. Witscript is a hybrid system. It uses machine learning modules, and those modules are within a rules-based framework. And it uses standard natural language processing and machine learning tools. So let's take a look at how Witscript actually writes a joke. The first step is Witscript takes a topic sentence, for example, an utterance in a dialogue. So a user might say to Witscript, TGI Fridays was fined $500,000 for serving cheap booze. So Witscript gets the topic sentence. And then Witscript, as a human would, selects the topic keywords. That is, the pair of nouns, noun chunks, or named entities that are the least similar in a relevant vector space. So to select the topic keywords, Witscript uses the natural language toolkit to do the sentence tokenization, the word tokenization, part of speech tagging, named entity recognition, all those tasks. And Once Witscript has identified the candidates for the topic keywords in the topic, Witscript uses Word2Vec to calculate which two candidates are the least similar in a relevant vector space, and those are the candidates that it selects as the topic keywords to base the joke on. The next step is Witscript. For each topic keyword, Witscript generates a list of associations, which are words that are the most similar in a relevant vector space. So Witscript, excuse me, Witscript takes the topic keyword TGI Fridays, and it uses Word2Vec, the most similar function of Word2Vec, to generate a list of associations like Applebee's, Dunkin' Donuts, Olive Garden, Red Lobster, other restaurants. Witscript takes the second topic keyword booze and uses Word2Vec to generate other associations: alcohol, drunken, liquor, beer. Once it has the lists of associations, Witscript creates a punchline by using wordplay to link an association from each list. So the TGI Fridays list of associations had as one association Dunkin' Donuts, a restaurant. It had on the list of associations for booze, it had the word drunken, and Witscript pairwise matches all possible associations from one list and the other list until it finds sufficiently satisfying wordplay, in this case, drunken and Dunkin', which is pretty good wordplay. So Witscript creates a punchline, Drunken Donuts, by substituting drunken for Dunkin'. So now Witscript has a punchline. The next step in building the joke is Witscript uses a fine-tuned language model to fill the blank between the topic sentence and the punchline with natural-sounding bridge words, or uses a pre-written template if the language model cannot come up with a decent enough set of bridge words. So in this case, the topic sentence is the TGI Fridays topic sentence. The punchline is Drunken Donuts, and the machine learning language model generates, in this case, the word not to bridge the topic sentence and the punchline, not Drunken Donuts. The neural network language model I'm using now is BERT, and BERT is pre-trained, and then I fine-tuned BERT on a set of roughly 37,000 late-night monologue jokes. So I fine-tuned BERT for comedy as best I could to generate the bridge words. Finally, to the bridge words and the punchline, Witscript adds pre-written filler words and then outputs the joke response if it meets a preset threshold for wordplay. So the user says, TGI Fridays was fined $500,000 for serving cheap booze. And Witscript says, TGI Fridays booze, yep, not Drunken Donuts. Okay, that's the joke. The bridge words, to the bridge words, Witscript has added TGI Fridays booze. So Witscript repeats the two topic keywords as part of the bridge. And then it adds a filler word, in this case, yup. The filler word is chosen at random from a list of possible filler words, and it just makes the output a little bit more conversational. So that's how Witscript writes a joke. Witscript factors these into its wordplay score. So when it's calculating the wordplay score, Witscript takes into account the phonetic edit distance between the two candidates, the two word candidates. It calculates whether there's alliteration. It looks at assonance between the two words. It also counts the number of stop consonants, and stop consonants are funny. Stop consonants are B, D, P, T, K, and I'm forgetting one, G probably, hard G. And it also takes into account some other factors in calculating its wordplay score. Witscript writes three types of wordplay jokes: substitution punchlines, juxtaposition punchlines, and portmanteau punchlines. And we'll see some examples of each of those in a minute. Before I get to the samples, a few points I'd like to make. That the user's utterances that you see in the examples were not in the training set. So this will be it was the first time that Witscript had any of this input to respond to. Witscript's responses were not edited by humans. So the words you see for Witscript are the words that actually came out of the program. But these jokes are subjectively in the top 10% in terms of funniness. So I went through all the jokes that Witscript wrote, and I just picked roughly the top 10%, or jokes that were in the top 10%. So I did some cherry picking of Witscript's output, which was already edited by Witscript itself. So here are some more sample jokes that Witscript wrote. Yesterday, Microsoft unveiled new eyewear that uses holograms. Microsoft eyewear, ha, watch Google Goggle. So this is a juxtaposition punchline. Witscript juxtaposed Google and Goggle to create the punchline, to just put the two words together that have wordplay. This is the 25th anniversary of the Blue Man Group. Blue anniversary? Well, so now it is the Blue Billy. So this is a portmanteau that Witscript created by taking blue and inserting that into Jubilee, which it figured out is an association of anniversary. Blue Billy. Now you can buy a $395 Mickey Mouse handbag. Mickey Mouse handbag? Yeah, just like a goofy purse. This is actually a substitution punchline. Witscript associated handbag with Gucci purse, and then Mickey Mouse with Goofy, and it substituted Goofy for Gucci.
That's awful.
It was awful. Oh, I think that's great wordplay. A goofy purse. All right, here's another one. A 56-year-old man is the world's first human to catch a rat disease. Rat disease, right. So now he wants to give cats cancer. Cats cancer, just words that it figured out were close enough. The wordplay was good enough, and it just juxtaposed the words to create the punchline. A man who claims he was bitten by a spider on an American Airlines flight is now suing. Spider flight, that's, wait for it, a flighter. So that's a portmanteau, fly plus spider. And this, by the way, is the only one of these examples that actually uses a template for the bridge words. That's, wait for it, came from a set of possible bridge templates. In that case, the machine learning language model didn't come up with anything acceptable, so it dipped into its store of templates. In Canada, a thief stole a woman's collection of 36 Barbie dolls. Dolls thief? Well, so not a Teddy theft. So that's substituting Teddy for petty and petty theft. A Teddy theft. I read that humans and Neanderthals may have had sex for millennia. Neanderthal sex? Yeah, thanks to a Pleistocene prostitute. Juxtaposition punchline. And finally, country music star Carrie Underwood is recovering from a broken wrist. Music wrist? Sure, so no clavicle music. Classical music is the association that it made with music, and it associated clavicle with wrist, so substituted clavicle for classical to get clavical music, which is very weird. But that's the joke. So what am I trying to do here? Am I trying to put late night TV comedy writers out of work with my software? No, this is what I'm trying to do. I'm trying to make an artificial intelligence more like a friend. So if you have an open domain chatbot, like Google has Mina now, Alexa has the Alexa Prize, open domain chat software, with a Witscript humor module, chatbots can have a sense of humor. They can be more relatable. Personal robots can be better companions, and human beings can be less lonely. And loneliness is now recognized as a really serious health problem. And this is a reflection of what I've been talking about in real life. This is a Wall Street Journal article from a few days ago. My girlfriend is a chatbot. Quarantine amid coronavirus could boost the nascent practice of seeking romance and friendship from artificial intelligence. So it's already happening. People are developing relationships with artificial intelligence. If you'd like to see the research poster form of what I just talked about, you can download it from 20lanemedia.com. And for a demo, contact me at 29media.com. The software is available for immediate license, and it is patent pending. And that concludes my prepared presentation. Let's see if
Joe, you had a couple of questions via the chat. Let me read out to
sure.
you. I'll read out to you. Did you try other language models other than BERT or other architectures? And did you use BERT out of the box or retrained with commenting material? I think you addressed that last part, but go ahead.
Sure. Am I still sharing my screen? Should I stop sharing? What do you think?
Now you can leave. Why don't you leave that sharing while you're speaking?
Sure. Okay. I'm sorry.
Show yourself talking.
Yeah, let me get this. Yeah, there we go. I'm sorry. Yes, I used BERT out of the box. I used the BERT large uncased model, which Google pre-trained on the books corpus and English Wikipedia. But then I did fine-tune BERT on the 37,000 late night monologue jokes, which I scraped off the internet. And yes, I did try other models other than BERT. Was that the other part of the question?
Yeah.
Yes, I did. I used for a while, I was trying an RNN LSTM model to generate the middle of the joke. I used a forward version of the model to do beam search, and then a backward version of the model to pick the best results from the text that it generated. But it didn't work very well, and it was hard to think of ways to use other text generators to accomplish the task, like GPT-2. Other text generators, you could start from a topic sentence and it would generate text, but the task is not to generate any text, it's to generate text from the topic that leads to a very specific punchline that the software has created. So you have to direct the text to end at a certain place, and I figured out that right now anyway, that BERT was the best way to do that, because one of BERT's specialties is filling in gaps, is filling in slots between sections of text, which is the task that I had. I had a punchline, I had a topic, and I needed to fill in text between them.
Yeah, there was a demo put out by, was it by the Hugging Face people, maybe 6 months ago, basically completion of phrases that someone had started using BERT. Anyway, you had what's really the same question asked in a number of ways. Is there a metric to decide the wittiness of a punchline based on the bridge word chosen? Someone else asked, what percentage of the output is reasonable humor? How do you decide if a joke is good enough? You want to address this question, metrics, how do you decide if a joke is good enough?
Well, Witscript decides that, and it's purely a function of how good the wordplay is. There's a wordplay score that Witscript comes up with for the punchline. It generates punchlines for each of the 3 kinds of jokes. In some cases, it's not successful. It doesn't have portmanteau jokes. It doesn't have a juxtaposition joke. It doesn't have a substitution joke. But most of the time, it'll come up with one option, and that'll have a number associated with it. And if the number meets a certain preset threshold, Witscript will output the joke. If it doesn't, Witscript says something like, "Sorry, I have no idea what's funny about this. Ask me something else." So it does eliminate the stuff that doesn't make any sense. It's totally worthless. So that's basically the answer. It's a number. The funniness is a number. It's the quality of the wordplay. It's the wordplay score.
Okay. So we do have another speaker, so we're going to move on, but Joe has his email address up here on the screen now, and I assume that he'd be welcoming of anyone who wants to send him a note with questions. Before we move to our next speaker, I do want to have a very short advertisement, if I can do it right. And that is this. So I produce conferences that are, unlike the meetup, not free. I have one coming up online in 3 weeks on May the 5th, the Emotion AI conference. Emotion AI is technologies that understand emotion and other affective signals in source material that can include text and also the spoken word, facial coding, and biometric signals via wearables and so on. That is an online conference taking place in the US Eastern Time Zone. And I hope you all will consider attending. You can check it out online at emotionai20.com. Our next speaker, Janna Lipenkova, will be one of the speakers on a different topic from the one that she's going to be talking about in just a moment at the conference coming up in 3 weeks. In 3 weeks, she's going to talk about health-related concerns in text, and in particular, in some ways relate this to the coronavirus COVID-19 situation. So a quick ad, I'd love to have you check out the conference. I am making a special discount available to Meetup members, a 20% discount. Just use the keyword Meetup when you register to get that discount. Please check it out. And now we will revert to our next speaker, and that is Janna Lipenkova from Anacode in Berlin. I will allow Janna to introduce herself however she wants. Will say I've known her for a number of years, including at Contexts, and I am really looking forward to what she has to say now. You should be able, Janna, you should be able to share your screen whenever you're ready. Oh no, I have to stop my own, sorry.
Can you see my screen now?
Give me a second. Yes, go ahead.
Okay, so yeah, we'll just start with the talk, and then it will also include a brief introduction of my company, I think. So basically, my talk today is about the automatic learning of lexical relations in highly dynamic domains, and we will also make this link between lexical relations on the one hand, and then ontologies and classifications of knowledge on the other hand. So it is a very applied talk or a perspective on the problem. This is why I will start with an introduction of the business challenge. And then from there, we will basically look down into the linguistic aspect of the matter. And specifically, I will focus on one lexical relation, which is the relation of hyperonymy. And then finally, I will present our own approach to hyperonymy discovery from text data. So first, the business challenge. So at my company, Anacode, we are doing web data mining for different challenges and questions in market intelligence for businesses. And one question or a request basically that we are getting more and more in the last 1 or 2 years is the monitoring, well, first the discovery, but then also the monitoring and the analysis of new technologies from online data, so online media, social media, but then also specialized blogs and media. So technologies such as artificial intelligence, blockchain, Internet of Things, and all the new hypes that we have out there in the world. So what are the challenges here from a linguistic standpoint? Basically, we have a highly dynamic data set with new concepts coming up all the time. And this also means that the whole conceptual framework is also very dynamic. It's changing quickly. So if you want to treat this or to capture it algorithmically, then you obviously need an algorithm that is able to learn this new knowledge pretty quickly. Some example questions that we get from our clients. So it can be from different departments, for instance, from strategy and planning. So what are the new trends and technological developments in my domain? It can be competitive intelligence. Are there any new substitutes emerging for my product? For investors, so like we are exploring the cybersecurity domain, and we are looking for investment targets specialized on different types of botnet attacks, and so on. So basically, you can see that these are like pretty different, really, questions, and we still need one unified underlying conceptual framework basically to target them. And the framework that we use is actually pretty classical. So we use ontologies, which are classifications of knowledge, and then with relations between the different classes and the different concepts. So here you can see a very small excerpt of an ontology for cybersecurity. At the top level, you see a cyber attack, which is a central notion in cybersecurity, and then you can see the more specific branches or classes. So you can see like network attack and botnet attack on the second level, and then you can also branch them down deeper into more fine-grained kinds of attacks. I know that ontologies are probably not the most fashionable framework in NLP now. So it's true that ontologies were like very relevant when we had all this time of expert systems in the 90s. But for us, basically these principles of organization of knowledge, so you have classification, you have hierarchical inheritance, actually they're kind of universals of how we as humans do organize our cognitive knowledge, and obviously also how we do reflect it in language. So this is why we basically chose this framework to work with our data. The challenge is obviously to make it adaptable and to be able to quickly learn new knowledge from data, basically in all these highly dynamic domains that we are talking about. And from here, we can make the switch to NLP and to linguistics, and specifically to this lexical relation of hyperonymy, which actually does reflect this classification relation in the ontology also. So hyperonymy is a lexical relation on a par with other relations, such as synonymy, meronymy, and so on. And basically, if we say that X is a hyponym of Y, or Y is a hypernym of X, then it means that X is a subclass, or it is a member of the class Y. Hyperonymy can apply to different parts of speech. So the classical, the prototypical one is probably nominal hyperonymy on nouns. So for instance, penguin is a kind of a bird, but you can also have it on verbs. So like walking is a kind of moving, and jiggling is a kind of laughing. You can have it on adjectives. Petite is a kind of small, or wine is a kind of red. Here, an important distinction or a remark. So hyperonymy obviously applies at the sense level and not at the lexem level. So in this, for instance, we have this example on adjectives. So wine is a kind of red. It only applies to the adjective meaning of wine, but doesn't apply to the nominal meaning of the beverage, basically. Logical properties of hyperonymy. So hyperonymy is transitive. If X is a hyponym of Y and Y is a hyponym of Z, then it means that X is a hyponym of Z, and it is asymmetric. So if X is a hyponym of Y, then Y cannot be a hyponym of X, but instead it is obviously a hypernym. So further down in the talk, basically, we will not yet address the relation of transitivity, because it's not really a linguistic characteristic of hyperonymy, but we will very much relate to this relation of asymmetricity. Okay, so far for the formal properties. Now, what is the linguistic distribution, and what are those properties that we can basically use in our text data to discover hyperonymy pairs? The first observation is that hyperonyms and hyponyms tend to occur together in some specific lexicosyntactic patterns. So these can be constructions like X, such as Y. So for instance, animals such as dogs. You can have X, especially Y, Y and other X, and so on. And in general, also in many collocations, so like nouns, adjectives, nouns, and so on. So we will see examples of this later. Then the second characteristic is, so when hyperonyms don't co-occur with their hyponyms, they still exhibit distributional similarity. So this is quite a logical property also, because if you imagine you have a classification of knowledge in a hierarchy with inheritance, then obviously the subclass does inherit some properties of the superclass. And this is also reflected in similar contexts in which the lexical items can be used. So we can see this example of an automobile engine. Basically it works, I would say so far more or less for all subtypes probably of automobiles. So you can have an SUV engine, electric car engine, and so on. And finally, so distributional similarity is a symmetric relation, but hyperonymy is even more specific in that it is asymmetric. And specifically, the hyponyms can occur in more specific contexts that are not shared by their hyperonyms. So we can have a sentence like, the dog is barking, but then if we replace dog by its hyperonym, animal, then the animal is barking doesn't work so well anymore, because basically bark is specific to dog. For animal, you have to take a higher level concept like, I don't know, making sounds or communicating, basically. So these are the linguistic properties, and in our approach, I will actually really follow these three properties and then show how we apply them and how we basically implement them in our algorithm. Okay, our approach. So let me first say something about the data set. So as said, we are very interested in extracting information about new technologies. So the data set that we used for this work is basically a corpus of 10 million English sentences, which we extracted from tech websites and then also partially business websites for 2 years, basically. So websites like TechCrunch, like The Verge, and so on. On the right here, you can see a very prototypical example. So you just like articles or blog posts from these websites. What are the characteristics? Well, first, it's obviously professional and curated writing, which means that it's relatively clean, coherent, and focused. It is a mix of tech and business content. So we could say that it is domain-specific data in a wide sense. But then on the other hand, as said, it is changing so quickly that, yeah, it's really hard to define what domain-specific data would be in this case. So you always have like many out-of-vocabulary words or multi-word expressions, and in general, of course, many proper names, many multi-word expressions, and so on. So I wouldn't say that it's a very clean data set in terms of its vocabulary in general. Okay, so now the approach in 4 steps, well, actually pre-processing and then 3 steps. So we have rule-based bootstrapping, which works exactly with this cooccurrence property. Then the 3rd step is distributional similarity. And in the 4th step, we basically model this asymmetry. And in the approach that I will present, we choose to model it exactly as context specificity, but there are also alternative approaches available to this. Okay, for the pre-processing, so we use linguistic pre-processing. We tried some more statistical approaches also, but then well, the experience is just that they really lose the linguistic information and the lexical information, the syntactic information that you would actually need to get these like conceptual relations between the items. So part of speech tagging, then dependency parsing, and then finally to account for the multi-word expressions, we also chunk the collocations and the multi-word expressions and then basically collapse them together in the preprocessed data. So the goal here is really to encode and also to keep the maximum of linguistic information and linguistic structure in the data. Then second step, rule-based bootstrapping for the cooccurrences. So here, let me start with an observation, quite interesting that we made, well, actually quite logical, but still interesting that we made it in the data about how the expression of hyponyms changes over the lifetime of a concept. So what our hypothesis was basically that when a new concept is introduced and it's not yet so established in the minds of readers, then it tends to co-occur with its hyperonym. Because obviously as a writer, if you want to be coherent, then you have to introduce and to somehow explain the new concept. And it turns out that one of the easiest kinds to provide additional information is actually to say to which class it belongs. And then as the concept becomes established with time, the frequency of the co-occurrences decreases. So let me give you an example, cryptojacking. So cryptojacking is a kind of a cyber attack that started in Q4 of 2017 as a malicious use of a person's computing power and so on. But you already see here, like very naturally, I also tend to say cryptojacking is a type of cyber attack. So to place it basically in its bucket in the ontology. And in the chart, you can see basically the time series for cryptojacking. So the gray area shows the proportion of the co-occurrences. So these are the times where cryptojacking basically occurs with cyber attack in its context. As a context, we use the paragraph here, so it's a pretty wide context. And the red area respectively shows those occurrences where it didn't co-occur with cyber attack. And as expected, you can see that the co-occurrences reduce basically over time as the concept becomes established. And the line in the chart also shows the average distance between hyperonym and hyponym, so between cryptojacking and cyber attack in words. And here you can also see that basically the distance is increasing, which means that the connection that the writer wants to make is basically also getting more and more loose. And this is a property that works very well for us empirically, because this is exactly the thing that we want actually to capture in our work. So we want to be able to capture these new concepts once they arise, when they are not yet established basically in the minds of readers, of our clients, and so on. So this is why we started with a very old-fashioned saying, Hearst patterns, developed by Maruti Hearst in 1992. But this is, again, a very universal linguistic tool, so it keeps coming up in the literature on ontology construction, on hyperonymy. So for instance, a paper by Roller et al. From 2018, it is actually one of the latest state-of-the-art papers on hyperonymy discovery. It relies exactly on this mechanism. So as said, basically these are lexical constructions like X such as Y, Y and other X, and so on. And we use them, so we implement them basically in the parse tree and then use them to extract possible candidate pairs for which we then measure different scores like the frequency, probability, point-wise mutual information, and so on. And second mechanism that we use is, as said, entailment in collocations. So these can be noun collocations or adjective noun collocations. And the observation here is that the collocation, in most cases, the collocation does entail the head. So if we have a security breach, then it also entails that it is a breach. Yeah, so that's a simple mechanism. A more interesting case is basically those collocations where just the modifier also entails the head. So for instance, denial of service attack, well, basically denial of service already entails attack. This doesn't work in all the cases, so you can have counter examples like in this table on the right, we can see some examples that we extracted using collocations like downgrade attack. So obviously downgrade by itself wouldn't entail the attack. Yeah, so this is something that basically doesn't work out of the box without further differentiation then of the candidate. Okay, so this was the Cooccurrence Parrot. Now we are coming to the second property, which is distributional similarity. So we did prototype different approaches to distributional similarity here. They turned out to work like pretty similarly in terms of the numbers and of the results that we got. So what we are using now is basically more or less plain word-to-vec, but trained on parsed data. So basically, which also then includes the information about the syntactic dependencies. And this is also a bit expected because in hyperonymy, we do want to capture functional similarity rather than obviously topical similarity. So in the chart, we can see basically a semantic map. So word vectors for attack in the sense of cyber attack, basically. And you can see here, so there is a legend below, and what you can see basically is that first the number of instances and the instances like Stuxnet, like NotPetya, and so on. And then also the number of actual hyponyms like DDoS, botnet, denial of service, and so on. So we have quite a high number of these instances, which would exactly give us those candidate pairs basically that we are looking for. So this is a positive result. The negative result obviously is that we also have other relations. So we have synonyms like, give me a synonym like, well, or near synonyms like cyber attack, infection, and so on. And then we also have other more or less unrelated stuff like cyber criminal, attacker, exploit, and so on. But actually, in general, you know, it's pretty much, so this is the knowledge that we want to capture in the ontology. So it's not necessarily hyperonymy, but still it's a nice side effect that this algorithm basically learns domain-specific data very well. Issue, as said, it's not necessarily hyperonymy because distributional similarity in itself is a symmetric relation, and hyperonymy is asymmetric, and there is this relation of specificity basically that we want to capture. And this is what we are doing here in the last step. So we chose context specificity as our measure for asymmetry, and the observation is obviously that hyperonyms are semantically more general than hyponyms, which also kind of means that they occur in more general and less informative contexts. And we can use this generality of the context basically as a measure then to distinguish. So if I have a candidate pair, is this like a good candidate for a hyperonymy relation or not in terms of the context specificity. So we use here context entropy as a measure for a specificity, and it is an approach that has already been proposed in the literature. So a score which is called SLQS. It is computed in 3 steps. So first step is basically that for each term you compute, well, for each context of a term, you compute the entropy of this context. And then for each term, you can basically build up, you can aggregate all the entropies of its context and then build the median of these entropies, which gives you kind of an index of the semantic generality of the term. And then when you have 2 terms, then basically you just compare these 2 context generality indices, and the one with the higher context generality obviously is more prone to be the hyperonym of the second term. And this is the last step basically that we're using so far. So I can't say that we are really like 100% happy with it, but in general, when you apply it really as the last step after the bootstrapping, after the distributional similarity modeling, then it does work pretty well. But so far, well, it's not an ideal solution. So the way we're applying it now, and I think many companies probably do try this kind of approach, is that we always do combine it obviously with manual curation of the ontologies. So we have knowledge engineers who work then on the manual curation and the manual basically checking of the results here. And so far from all the prototyped approaches, basically this sequence of steps, it gave us the best results then also in terms of the numbers. Okay, to sum up, so basically I presented a hybrid approach to hyperonymy discovery, which benefits from the lexical and the linguistics characteristics of hyperonymy, and so it can learn hyperonymy in an unsupervised fashion from the data. So we use lexicosyntactic patterns for bootstrapping, then in the second step, distributional similarity for capturing the nearest neighbors of hyperonyms and co-hyponyms. And then finally, this entropy-based approach then also to discriminate among the candidates that we captured with the distributional similarity, and then to find out which terms are more specific and then are more prone to be the hyponyms. So as I said, but just to emphasize again, this works like really well with this temporal evolution that we saw in the use or co-use of hyponyms and hyperonyms basically that we see specifically in our data set. Challenges and future work, well, obviously, as said, so far it's very empirical, so it's always like an interplay then with human curation. So one basic challenge would be really to have an evaluation strategy, but it's not an evaluation strategy just on one baseline data set, more or less. Instead, it really has to take into account all the changes that occur in this data set. And then an additional step that we want to try basically additionally, so at the end of this pipeline, is hyperonymy specific manipulations on a vector space. So there have been multiple proposals in the last 2 years about how you can basically model and bias the vector space in such a way that it kind of pulls together the hyperonyms with their hyponyms, and this way basically it emphasizes the similarity or the relations between specifically this lexical relation. That's it. Thank you.
Janna, thank you. You have a couple of questions. One is in the Q&A and the other is in the chat. Let me read it to you from the chat first. We have Ryan Gendubi asking, in distributional similarity, how do you establish how many levels of the ontology you need to roll up to get to the same concept? In the example you gave, you had engine associated with SUV, electric car, and another road vehicle. But an airplane also has an engine. So how do you avoid inferring that an airplane is also a road vehicle?
Mm-hmm. Okay, so this would be, well, it can relate to the semantic to the formal relation of transitivity, but then also Yeah, well, basically in this case, obviously you wouldn't be able just to do it like by this example of the engine. So you would need other, to consider basically other similarities also, like what's the kind of movement that the vehicle is producing. So is it flying or is it like on Earth movement and so on? Yeah, so you would obviously need to consider then a set of the similarities and of the related terms then to this word.
All right, so further information. We have a question from Nelson Silva. Hurst patterns require the creation of many rules and are dependent on the type of text content domain. How do you create your patterns?
Well, so Hurst proposed a set of 70 patterns, so that's obviously enough for a start. Exactly, 70 patterns. Then, I mean, a pretty classical approach again to bootstrapping is that we take the hyperonymy pairs that we're already like certain of, where we have a high confidence, and then again we reuse them to bootstrap even more patterns. So we look for those syntactic constructions in which they occur more frequently than usual.
All right, one more question from Naeem Tyson. Have you tried to use the word-to-vec embeddings, create a dissimilarity matrix, and use the hierarchical clustering for your ontology?
Okay, that I must note it down because no, we haven't tried it yet. So dissimilarity matrix and then hierarchical clustering. We haven't tried it yet. Thanks a lot for the suggestion.
Okay, and if people want to get in touch with you, you don't have your email address up on this slide. They should get in touch with you how?
I can put it on the slides and then forward you the slides again.
That'd be fine. Why don't you type if you can do it, type your email address into the chat so that people can get in touch with you. Let's do one more question that just came in and then we'll wrap up. So Sai Goli asks, well, two parts, how to normalize words, phrases expressed in different ways, such as Microsoft Word, Word, MS Word to mean the same thing. Okay, we have classic co-reference question here. And then secondly, best way to cluster words based on word-to-vec embeddings for knowledge discovery. So the first question is about co-reference.
Yeah. Yeah, so the first question basically, yeah, that's co-reference or maybe synonymy or near synonym. Yeah, so for this we would basically, as you saw it, the synonyms also do occur in the result of the word-to-vec, yeah, and then what we need is just an additional mechanism basically to distinguish then in this map to distinguish between the hyperonyms and then other kinds of relations such as synonymy. Okay, second question was?
Best way to, it's in Q&A, best way to cluster words based on word-to-vec embeddings for knowledge discovery.
Based on word-to-vec embeddings.
Well, the word yeah.
Yeah.
It's addressed to you.
Yeah, that's kind of a difficult question. So first I would really ask, I mean, what kind of knowledge discovery do you want to do? So do you need like topical knowledge or functional knowledge? In our case, it's functional knowledge. So in our case, like in terms of word-to-vec, our choice was just to go with dependency-based word embeddings. But then you still need some additional mechanisms basically to really discover the knowledge there.
Okay, I have your email address and I will type it into the chat right now so that people can follow up. So great. Thank you very much, Janna, for participating today. I'm looking forward to your participation in 3 weeks in the Emotion AI conference. And so I will mention that before then, again, we have another online NLP meetup on Monday, April the 27th, so in 2 weeks. And that is at 1 p.m. US Eastern. So it is an accessible time for attendees who are in Europe and in the US Pacific time zone as well. So I hope you all can join us. That's listed on the DC NLP and the New York NLP meetups. And I will we'll see about getting the partner meetups to list it as well. So thanks everyone for attending today, and we're going to wrap up now. Oh, and thanks once again to our two speakers, Janna Lipenkova and Joe Toplyn.
Thank you, Seth. Thanks a lot also.